In the very beginning, there was nothing at all. No space, no time, no matter, no energy. Just an infinitely dense point containing everything that would ever exist. Physicists call this the singularity, though the word feels too grand for something smaller than the smallest thing you can imagine. 13.8 billion years ago, this point began to expand. Not an explosion into space, but rather the creation of space itself, unfolding like a flower that had always been waiting to bloom. The universe doubled in size, then doubled again and again and again, all within a fraction of a second, so small that even speaking its duration would take longer than the duration itself. This period is called cosmic inflation. In less time than it takes light to cross the width of a proton, the universe expanded from smaller than an atom to perhaps the size of a grapefruit. During this expansion, quantum fluctuations, tiny ripples in the fabric of reality, were stretched across cosmic distances. These ripples would eventually become the seeds of galaxies, billions of years later. The temperature during these first moments was unimaginably hot, 10 to the 32 degrees Kelvin, a number with 32 zeros after it. At this temperature, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. There was no distinction between them yet. As the universe continued expanding, it began to cool. When it cooled to around 10 to the 28 degrees, gravity separated from the other forces, becoming distinct and independent. The universe was now 1/1,000,000th of a second old. By the time 1/10,000th of a second had passed, the universe had cooled enough for quarks to begin forming. Quarks are the fundamental building blocks of matter. Though they never exist alone in nature, they always bind together in groups. In the universe's first moments, they swam freely in a hot, dense soup of particles and radiation called the quark-gluon plasma. When the universe reached 1/1,000,000th of a second old, it had cooled to about 10 trillion degrees Kelvin. At this temperature, quarks began binding together permanently, forming protons and neutrons. This moment is called the quark epoch's end. Every proton in every atom in your body was formed in this first microsecond of cosmic time. For the next 3 minutes, the universe underwent primordial nucleosynthesis. Protons and neutrons collided and fused, creating the first atomic nuclei. Most combined to form hydrogen nuclei, simply single protons. About 1/4 of the universe's matter became helium nuclei, each containing 2 protons and 2 neutrons. Trace amounts of lithium and beryllium also formed. These 3 minutes determined the chemical composition of the universe for hundreds of millions of years to come. Roughly 75% hydrogen, 25% helium, and the tiniest whisper of other light elements. This ratio would remain unchanged until the first stars formed and began cooking heavier elements in their cores. After these eventful first minutes, the universe entered what might be called a waiting period. It continued expanding and cooling, but nothing particularly dramatic happened. Particles bounced off each other. Photons, particles of light, scattered constantly off free electrons, unable to travel any distance without colliding with something. The universe during this time was opaque, like being inside a fog so thick you cannot see your own hand. Light existed everywhere, bouncing frantically between particles, but it could not travel freely. If you could have opened your eyes during this period, you would have seen only a blinding, uniform glow in every direction. This era is called the photon epoch, and it lasted for approximately 380,000 years. During this time, the universe was a democracy of radiation and matter, with neither clearly dominant. The temperature slowly decreased from millions of degrees down to about 3,000 degrees Kelvin, roughly half the temperature of the sun's surface today. Then something extraordinary happened. At around 380,000 years after the beginning, the universe had cooled enough for electrons to be captured by atomic nuclei. Hydrogen nuclei captured electrons to become complete hydrogen atoms. Helium nuclei captured electrons to become helium atoms. This moment is called recombination. Though the name is misleading, these electrons and nuclei had never been combined before. When electrons were captured by nuclei, something profound occurred. With free electrons no longer blocking their path, photons could suddenly travel freely through space. The universe became transparent for the first time. Light could finally journey across cosmic distances unimpeded. These first free photons are still traveling today. Over the past 13.8 billion years, the universe's expansion has stretched their wavelengths, cooling them from visible light into microwaves. We detect this ancient light as the cosmic microwave background radiation, a faint glow coming from every direction in space, the afterglow of creation itself. The cosmic microwave background is remarkably uniform, showing the same temperature in all directions to within 1 part in 100,000. But within that uniformity lie tiny variations, slight differences in temperature of just a few millionths of a degree. These tiny ripples represent the quantum fluctuations from inflation, now stretched to cosmic size. They mark the denser regions where gravity would eventually pull matter together to form the first structures. After recombination, the universe entered what cosmologists call the Dark Ages. With no stars yet born, no galaxies yet formed, the universe contained only neutral hydrogen and helium gas, slowly collapsing under gravity into the denser regions marked by those tiny temperature variations in the cosmic microwave background. The temperature of the universe during the Dark Ages was actually quite pleasant by human standards. Within a few million years after recombination, the cosmic background radiation had cooled to around 300 degrees Kelvin. Warm, but not unbearably so. Eventually it cooled further to temperatures that would feel comfortable to human skin, though of course no humans existed, nor planets, nor stars. During this period, space was filled with vast clouds of hydrogen and helium, slowly contracting under their own gravity. The clouds were not uniform. Some regions were slightly denser than others, and these denser regions had stronger gravitational pull, attracting more matter, becoming denser still. This process is called gravitational instability, and it is the mechanism by which all structure in the universe forms. As these clouds collapsed, they began to fragment into smaller pieces. Each fragment continued collapsing on its own, and these fragments fragmented further, creating a hierarchy of structures collapsing at different scales. The largest fragments would eventually become galaxy clusters. Medium-sized fragments would become individual galaxies. The smallest fragments would become the first stars. The Dark Ages lasted for approximately 100 million years, though the exact timing is still debated. During all this time, the universe contained no sources of visible light. If you could have traveled through this cosmic night, you would have seen only the fading infrared glow of the cosmic background radiation, growing dimmer and redder as the universe expanded and cooled. Near the end of the Dark Ages, the first clouds of hydrogen gas had collapsed to the point where their cores became incredibly dense and hot. When a cloud's core reaches about 10 million degrees Kelvin, something miraculous occurs. Hydrogen nuclei, protons, begin fusing together, releasing tremendous amounts of energy. This is nuclear fusion, the power source of stars. The first stars likely formed around 100 to 200 million years after the beginning. These were not stars like our Sun. They were monsters, perhaps 100 or even 300 times the Sun's mass. Stars this massive burn incredibly hot and bright. with surface temperatures exceeding 50,000 degrees Kelvin. They shone with a harsh, blue-white light. These first stars are called population 3 stars, though somewhat confusingly, they were actually the first population, not the third. Astronomers have never directly observed a population 3 star. They formed so long ago and lived such brief lives that none should exist in the universe today. But their influence shaped everything that came after. Population 3 stars were made almost entirely of hydrogen and helium, with almost no heavier elements. This is because heavier elements had not yet been created. They would be forged in the cores of these first stars through nuclear fusion and scattered into space when these stars died. But that comes later in our story. When the first stars ignited, they did not simply shine in isolation. Their ultraviolet radiation began to affect the hydrogen gas surrounding them, stripping electrons from hydrogen atoms in a process called reionization. This transformed the neutral hydrogen that had existed since recombination back into ionized hydrogen, separate protons and electrons. The process of reionization did not happen all at once. It began in isolated pockets around the first stars and slowly expanded outward, like ink spreading through water. Over the course of several 100 million years, these ionized bubbles grew and merged until eventually the entire universe had been reionized. The Dark Ages had ended. The first stars lived fast and died young. A star with 100 times the Sun's mass might live only 2 million years before exhausting its nuclear fuel. When these massive stars died, they did so catastrophically, as supernovae. Explosions so bright they can briefly outshine entire galaxies. These supernova explosions served a crucial purpose. Inside the cores of massive stars, nuclear fusion creates heavier elements. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on, building up the periodic table element by element. When a star explodes, it scatters these newly created elements into space. The very first generation of stars thus enriched the universe with elements that had never existed before. Carbon, nitrogen, oxygen, silicon, iron, all the elements necessary for planets and life were first manufactured in the cores of population 3 stars and dispersed by their deaths. The debris from these exploding stars mixed with clouds of pristine hydrogen and helium, creating a new generation of stars with slightly different compositions. These second-generation stars, called population 2 stars, contain small amounts of heavier elements in addition to their mostly hydrogen and helium makeup. They were generally less massive than their predecessors, and therefore longer lived. Around this same time, between 200 and 500 million years after the beginning, the first galaxies began to form. A galaxy is not simply a random collection of stars. It is a gravitationally bound system, often containing hundreds of billions of stars, along with gas, dust, and dark matter, all orbiting a common center. The first galaxies were much smaller than modern galaxies. They might have contained only a few million stars, compared to the hundreds of billions in today's giant galaxies. But they were the seeds from which larger structures would grow. Gravity drove the evolution of these early galaxies. Smaller galaxies merged with other small galaxies, forming larger ones. This process is called hierarchical structure formation, and it continues today. Galaxies are not static objects, but dynamic systems that grow through mergers and accretion. Many early galaxies contain supermassive black holes at their centers. These black holes formed in ways that are still not entirely understood. Some may have grown from the collapsed cores of population 3 stars. Others may have formed directly from collapsing gas clouds. Regardless of their origin, they grew rapidly by accreting matter from their surroundings. When matter falls into a supermassive black hole, it does not fall directly in. Instead, it forms a spinning disk of material around the black hole, called an accretion disk. Friction in this disk heats the material to millions of degrees, causing it to emit enormous amounts of radiation. These actively feeding black holes are called quasars, and they were among the brightest objects in the early universe. The brightest quasars could shine with the light of trillions of suns. Their radiation could influence star formation across their entire host galaxy, both triggering it in some regions and suppressing it in others. The interplay between supermassive black holes and their host galaxies is one of the fundamental processes shaping the evolution of galaxies. By around 500 million years after the beginning, the universe had transformed dramatically from its state during the Dark Ages. Instead of dark clouds of neutral hydrogen, space now contained millions of small galaxies, each hosting millions or billions of stars. The reionization process was well underway. The universe had become a place of light. The stars forming during this era were beginning to show more variety in their masses and compositions. Along with massive stars that would live brief, violent lives, smaller stars were forming. Stars that would burn their fuel slowly and steadily, living for billions or even trillions of years. Our Sun is one of these smaller, longer-lived stars, though it would not form for another 9 billion years. Between 500 million and 1 billion years after the beginning, galaxies continued to grow through mergers. When two small galaxies collided, their stars would rarely hit each other. Space within a galaxy is mostly empty, but their gas clouds would collide, compress, and trigger bursts of new star formation. These merger-driven starbursts could create millions or billions of new stars in a relatively short time. The resulting galaxies would shine brilliantly in ultraviolet and visible light from massive young stars, while also glowing in infrared from the dust heated by starlight. These starburst galaxies were the construction sites where much of the universe's stellar content was built. Around 1 billion years after the beginning, galaxies had grown to masses comparable to or exceeding our present-day Milky Way. Large spiral galaxies had begun to form, with their characteristic rotating disks and spiral arms. Elliptical galaxies, smooth, featureless collections of old stars, had also emerged, often as the products of major galaxy mergers. The universe at this age looked remarkably different from today, but also surprisingly similar. The same physical processes that shaped galaxies then still shape them now. Stars still form in cold, dense molecular clouds. Massive stars still explode as supernovae, enriching space with heavy elements. Galaxies still merge and interact. The fundamental mechanisms were established early and have continued for over 12 billion years. By 1.5 billion years after the beginning, the universe had entered what might be called its middle age, though it was still quite young. The rate of cosmic star formation had begun its long climb toward a peak that would occur around 3 billion years after the beginning. This epoch, when star formation was at its maximum, represents the universe's most productive era. During this peak period, stars were forming at a rate perhaps 10 times higher than today. Nearly every galaxy was actively making new stars. The universe was bright, busy, and creative. Most of the stars that exist today, including our Sun, were formed during this peak era or shortly thereafter. The gas between galaxies, called the intergalactic medium, was not empty during this time. It contained vast quantities of hydrogen and helium, enriched with small amounts of heavier elements scattered by the first generations of supernovae. This enriched gas would be pulled into galaxies by gravity, fueling ongoing star formation. Some of this intergalactic gas was heated to extremely high temperatures by shock waves from supernovae, and by radiation from quasars. At temperatures of millions of degrees, this gas emits X-rays. Observations show that much of the ordinary matter in the universe exists in this hot, diffuse form, spread between galaxies in vast cosmic filaments. These filaments are part of the large-scale structure of the universe, often called the cosmic web. On the largest scales, matter is distributed not uniformly, but in a network of dense filaments surrounding vast empty regions called voids. Galaxies form primarily along these filaments, like beads on a string. The cosmic web structure reflects the initial density variations present in the cosmic microwave background. Those tiny ripples from inflation, stretched to cosmic scale, determined where matter would collect and where it would be absent. The structure of the universe on the largest scales was thus set in the first fraction of a second after the beginning. Between 2 and 4 billion years after the beginning, many galaxies began developing distinct structures. Spiral galaxies formed rotating disks with spiral arms, where most star formation occurred. These arms are not permanent structures, but density waves, regions where stars and gas temporarily bunch together as they orbit the galactic center. The spiral arms appear bright because massive young stars, which form from gas compressed in the density waves, shine intensely but briefly. By the time these massive stars die, they have orbited out of the spiral arm where they formed. The spiral pattern thus persists even as individual stars move through it, like a wave on water that maintains its shape while the water molecules themselves move up and down. Other galaxies evolved into elliptical shapes, containing older stellar populations and little ongoing star formation. These ellipticals often formed through major mergers between spiral galaxies. During such mergers, the orderly rotation of the spiral disks is disrupted, and the stars end up on random orbits, creating the smooth, rounded appearance of elliptical galaxies. Some galaxies developed large central bars, elongated structures of stars extending across the galactic center. The Milky Way itself contains such a bar. These bars can funnel gas toward the galactic center, affecting both star formation rates and the feeding of central supermassive black holes. By 4 billion years after the beginning, galaxy clusters, groups of hundreds or thousands of galaxies bound together by gravity, had fully formed. The space between galaxies in a cluster is filled with extremely hot gas, heated by the gravitational energy released as the cluster formed. This intracluster gas can be more massive than all the stars in all the galaxies combined. Around 5 billion years after the beginning, the universe had reached its peak era of star formation. Across billions of galaxies, massive molecular clouds were collapsing to form new stars at a prodigious rate. The universe has been slowly winding down from this peak ever since. Molecular clouds are the birthplaces of stars. These clouds contain primarily molecular hydrogen, 2 hydrogen atoms bonded together, along with small amounts of other molecules and microscopic dust grains. They are cold, typically only 10 to 20 degrees above absolute zero, and dense compared to their surroundings, though still far more diffuse than Earth's atmosphere. Within these molecular clouds, tiny variations in density can trigger gravitational collapse. Perhaps a shock wave from a nearby supernova compresses part of the cloud. Perhaps 2 clouds collide. Whatever the trigger, once a region begins to collapse under its own gravity, the process becomes self-reinforcing. As the cloud collapses, it fragments into smaller pieces. Each fragment continues collapsing independently, eventually forming a protostar, a ball of gas that is not yet hot enough in its core for nuclear fusion to begin. The protostar continues to accrete material from the surrounding cloud, growing in mass. Material falling onto a protostar does not fall directly onto its surface. Due to conservation of angular momentum, the material forms a rotating disk around the protostar, called a protoplanetary disk. Material from this disk gradually spirals inward, feeding the growing protostar at its center. The protostar phase can last several million years. During this time, the protostar is warm and glowing, but its energy comes from gravitational contraction, not from nuclear fusion. It slowly heats up as it contracts, its core temperature steadily rising. When the core temperature reaches approximately 10 million degrees Kelvin, hydrogen fusion ignites. The protostar becomes a true star, entering the main sequence phase of its life, the longest and most stable phase, during which it will fuse hydrogen into helium in its core for billions of years. The mass of a star determines almost everything about its life. A star with 10 times the Sun's mass will shine 1,000 times brighter, but live only 20 million years. A star with 1/10 the Sun's mass will shine 1,000 times fainter, but live over 1 trillion years. Mass determines luminosity, temperature, color, lifespan, and ultimate fate. Most stars that form are red dwarfs, small stars with masses between about 8% and 40% the mass of the Sun. Red dwarfs burn their fuel so slowly that even the oldest red dwarfs, formed within the first billion years of the universe, are still on the main sequence today. They will continue shining for trillions of years into the future. Our Sun, which formed around 9 billion years after the beginning, is more massive than average. It has a mass of 1.989 times 10 to the 30th kilograms. About 73% of this mass is hydrogen, 25% is helium, and the remaining 2% consists of heavier elements. Astronomers somewhat confusingly call all elements heavier than helium metals, even though many are not metallic. The Sun's metallicity, its percentage of heavy elements, indicates it is a population 1 star, formed from gas that had been enriched by multiple previous generations of stars. The heavy elements in the Sun, and in the planets that formed around it, were all created in earlier stars and scattered into space when those stars died. In the Sun's core, where temperatures reach 15 million degrees Kelvin, and pressures are 250 billion times Earth's atmospheric pressure, hydrogen fuses into helium through a process called the proton-proton chain. 4 hydrogen nuclei eventually combine to form 1 helium nucleus, with a small amount of mass converted to energy according to Einstein's famous equation E equals mc squared. The energy released by fusion in the Sun's core must work its way outward through the Sun's interior. This journey takes approximately 1 million years. Photons are absorbed and re-emitted countless times as they diffuse through the dense solar interior, gradually working their way from the core to the surface. Once photons reach the Sun's surface, they escape into space at the speed of light. The photons we see when we look at the Sun were emitted from its surface about 8 minutes ago, but the energy they carry was released in fusion reactions in the core around 1 million years ago. Sunlight carries ancient energy to Earth. The Sun has been shining steadily for approximately 4.6 billion years and will continue for about another 5 billion years. During this main sequence phase, it slowly increases in brightness as helium accumulates in its core. The Sun today is about 30% brighter than when it first formed. When the Sun exhausts the hydrogen in its core, around 5 billion years from now, it will begin fusing hydrogen in a shell surrounding the core. This will cause it to expand dramatically, becoming a red giant star. It may expand to engulf the orbits of Mercury and Venus, and possibly Earth, though the details are uncertain. During its red giant phase, the Sun will fuse helium into carbon and oxygen in its core. However, it is not massive enough to fuse these elements further. Eventually, after perhaps 1 billion years as a red giant, it will gently shed its outer layers, creating a planetary nebula, a glowing shell of gas illuminated by the hot core left behind. This remnant core is called a white dwarf. A white dwarf contains roughly the Sun's mass, compressed into a volume about the size of Earth. It no longer undergoes fusion, but slowly cools over trillions of years, eventually becoming a cold, dark sphere of carbon and oxygen, a black dwarf, though the universe is not yet old enough for any black dwarfs to exist. More massive stars follow a different path. A star with 8 times the Sun's mass or more will fuse hydrogen, then helium, then carbon, then neon, then oxygen, then silicon, building up layers of different elements like an onion. Each successive stage of fusion happens faster than the previous one. Silicon fusion produces iron, but iron cannot be fused to release energy. Iron is at the peak of the binding energy curve. Fusing iron nuclei together would require energy rather than release it. When a massive star's core becomes iron, fusion stops. The core can no longer support itself against gravity. The core collapses catastrophically in less than 1 second, from the size of Earth to about 20 kilometers across. The collapse releases a tremendous amount of gravitational energy, more energy than the star has emitted during its entire previous life. This energy drives a shockwave outward through the star's outer layers, blowing them into space in a supernova explosion. The explosion synthesizes new elements as well. Elements heavier than iron, such as gold, platinum, and uranium, are created during supernovae through rapid neutron capture. Every gold ring, every uranium atom, was forged in a supernova explosion billions of years ago. What remains of the core after a supernova depends on its mass. If the core is between about 1.4 and 3 times the Sun's mass, it becomes a neutron star, a sphere about 20 kilometers in diameter, composed almost entirely of neutrons, packed so tightly that a teaspoon of neutron star material would weigh billions of tons. Neutron stars often rotate rapidly, sometimes hundreds of times per second. If a neutron star's magnetic field is aligned appropriately, it can emit beams of radiation that sweep across space like lighthouse beams. When Earth lies in the path of these beams, we observe regular pulses of radiation. These objects are called pulsars. If the collapsing core is more massive than about 3 times the Sun's mass, not even neutron pressure can halt the collapse. The core continues collapsing until it forms a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape from within a boundary called the event horizon. Black holes are not cosmic vacuum cleaners that suck in everything nearby. They affect their surroundings through gravity, just as any massive object does. If the Sun was suddenly replaced with a black hole of the same mass, Earth would continue orbiting just as before, though it would be quite cold and dark. Supermassive black holes, millions or billions of times the Sun's mass, reside at the centers of most large galaxies. The Milky Way contains a supermassive black hole called Sagittarius A star, with a mass of approximately 4 million suns. It lies about 26,000 light-years from Earth, in the direction of the constellation Sagittarius. Sagittarius A star is relatively quiet today, accreting material only slowly. But observations of stars orbiting close to it have allowed astronomers to determine its mass with high precision. These stars move at speeds exceeding 5,000 kilometers per second. Their orbital periods measured in years, even though they travel distances comparable to the size of our solar system. The Milky Way itself is a barred spiral galaxy containing approximately 200 to 400 billion stars. It measures about 100,000 light-years across, a light-year being the distance light travels in 1 year, roughly 9.5 trillion kilometers. Our solar system orbits within the Milky Way at a distance of about 26,000 light-years from the galactic center. We orbit at a speed of roughly 230 kilometers per second, completing one orbit approximately every 225 million years. The solar system has completed about 20 orbits since its formation. The story of our solar system begins approximately 9 billion years after the universe itself began, in a dense molecular cloud in one of the Milky Way's spiral arms. This cloud, composed mostly of hydrogen and helium, but enriched with heavier elements from previous generations of stars, was cold and dark, perhaps disturbed by the shockwave from a nearby supernova explosion. The disturbance triggered gravitational collapse in one region of the cloud. Over the course of perhaps 100,000 years, this region contracted, spinning faster as it shrank due to conservation of angular momentum. Most of the mass collected at the center, forming what would become our Sun. But not all the material fell directly into the growing Sun. Material in the outer parts of the collapsing cloud had too much angular momentum to spiral directly inward. Instead, it formed a flattened, rotating disk around the young protostar, the solar nebula from which all the planets would eventually form. The solar nebula was vast, perhaps several hundred times the distance from Earth to the Sun. In its inner regions, close to the hot protostar, temperatures exceeded 1,000 degrees Kelvin. In the outer regions, temperatures dropped to only a few tens of degrees above absolute zero. This temperature gradient determined what kinds of materials could condense at different distances. Close to the Sun, only materials with very high melting points could condense into solid particles. These were primarily metals like iron and rocky materials like silicates. Volatile materials, water, methane, carbon dioxide, and others that vaporize easily remained as gases in the hot inner solar system. Beyond a certain distance from the Sun, called the frost line or snow line, temperatures were low enough for water ice to condense. This frost line lay at approximately 3 to 4 times Earth's distance from the Sun. Beyond it, icy materials were abundant. Inside it, they existed only as vapor. Within the solar nebula, tiny dust grains stuck together when they collided, gradually building larger and larger aggregates. This process, called accretion, proceeded slowly at first. Dust grains grew into pebbles, pebbles into boulders, boulders into kilometer-sized objects called planetesimals. The planetesimals were numerous enough that their combined gravity became significant. This accelerated the accretion process. Larger planetesimals, with stronger gravity, grew faster by attracting smaller ones. Through a combination of gradual accretion and occasional violent collisions, planetesimals merged into larger and larger bodies. In the inner solar system, these growing bodies had access only to the relatively small amounts of rocky and metallic material available there. The terrestrial planets, Mercury, Venus, Earth, and Mars, formed from these limited materials, and consequently remained relatively small. Mercury, closest to the Sun, accreted into a planet with a mass only about 5% that of Earth. Its proximity to the hot young Sun likely caused much of its lighter rocky material to evaporate, leaving Mercury unusually rich in iron for its size. Its large iron core comprises about 60% of the planet's mass. Venus and Earth, forming at slightly greater distances where more material was available, grew larger. Venus reached about 82% of Earth's mass. Earth itself grew to its present mass of approximately 5.97 times 10 to the 24th kilograms. Mars, forming near the outer edge of the terrestrial planet region, where material was sparser, grew to only about 11% of Earth's mass. Its small size may have been influenced by Jupiter's gravity, which stirred up the nearby region, increasing collision speeds and making it harder for Mars to accrete material efficiently. Beyond the frost line, the situation was very different. Here, rocky and metallic materials were supplemented by abundant ices, water ice, methane ice, and ammonia ice. With more raw material available, bodies could grow much larger. Jupiter formed at about 5 times Earth's distance from the Sun. It likely began as a rocky core that grew to several times Earth's mass. When this core reached approximately 10 Earth masses, its gravity became strong enough to attract and hold on to the light gases, hydrogen and helium, from the surrounding nebula. Gas accreted onto Jupiter's core rapidly, perhaps over only a few thousand years. Jupiter grew to over 300 times Earth's mass, becoming the largest planet in our solar system. Despite this enormous mass, most of Jupiter is composed of hydrogen and helium, giving it a relatively low average density, only slightly more than water. Saturn formed similarly, but slightly more slowly, perhaps because there was less material available at its greater distance from the Sun. It reached about 95 times Earth's mass, substantial, but only about 30% of Jupiter's mass. Like Jupiter, it is composed mostly of hydrogen and helium surrounding a rocky core. Uranus and Neptune, the ice giants, formed even farther from the Sun, where the solar nebula was increasingly sparse. They likely took much longer to form than Jupiter and Saturn. Current models suggest they may have formed closer to the Sun and later migrated outward to their current positions. These two planets contain much more ice and rock relative to hydrogen and helium than Jupiter and Saturn. Each has a mass roughly 15 to 17 times that of Earth, but unlike the gas giants, much of this mass consists of water, methane, and ammonia ices surrounding a rocky core, with only a relatively thin atmosphere of hydrogen and helium. During the early stages of planet formation, the solar system was a chaotic, violent place. Countless planetesimals careened through space on intersecting orbits. Collisions were frequent, some mergers creating larger bodies, others shattering objects into fragments. One of these collisions fundamentally shaped Earth's character. Approximately 50 to 100 million years after the solar system began forming, when Earth had grown to roughly its present size, a Mars-sized body, now called Theia, struck Earth in a glancing blow. The impact released enough energy to vaporize both Theia and a substantial portion of Earth's mantle. Rock vapor, along with fragments from both bodies, was thrown into orbit around Earth. Over time, perhaps as quickly as a few years or as slowly as a century, this orbiting material coalesced to form the Moon. The Moon is thus made of material from both Earth and Theia. This explains why lunar rocks have similar oxygen isotope ratios to Earth rocks. They came from the same source. The impact also likely set Earth spinning rapidly and established the tilt of its rotation axis. The Moon formed quite close to Earth, perhaps only 15,000 to 30,000 kilometers away, compared to its current distance of about 384,000 kilometers. It appeared enormous in Earth's sky, perhaps 15 to 20 times larger than it appears today. Tidal forces between Earth and Moon have gradually pushed the Moon away over billions of years. The Moon continues receding today at about 3.8 centimeters per year. In the distant past, when the Moon was closer, its gravitational influence raised enormous tides on Earth, hundreds of meters high, though Earth's early oceans may not yet have existed when the Moon first formed. The early solar system contained far more small bodies than it does today. The asteroid belt, located between Mars and Jupiter, may have contained several Earth masses of material originally. Today, it contains less than 1/20th of Earth's mass, the rest having been scattered or accreted into planets. Jupiter's gravity prevented the asteroids from accreting into a planet. Its gravitational influence stirred the asteroid belt, increasing collision velocities to the point where impacts tended to shatter bodies rather than allow them to merge. Over billions of years, most of the original asteroid belt material was lost, leaving only the remnants we see today. Beyond Neptune lies the Kuiper Belt, a region containing countless icy bodies, remnants from the solar system's formation that never accreted into planets. The Kuiper belt extends from Neptune's orbit at about 30 times Earth's distance from the Sun to perhaps 50 times that distance. Pluto, discovered in 1930 and considered the ninth planet until 2006, is the most famous Kuiper belt object. It has a mass less than 1/500th that of Earth and shares its orbital region with thousands of similar objects. This led to its reclassification as a dwarf planet, a decision that recognized the Kuiper belt's true nature as a population of many small bodies rather than a single anomalous planet. Even more distant is the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system. This cloud likely extends halfway to the nearest star, approximately 1 light-year from the Sun. It contains perhaps trillions of objects, though direct observation of Oort cloud objects is nearly impossible due to their extreme distance and small size. The Oort cloud is the source of long-period comets. Occasionally, the gravity of a passing star disturbs an Oort cloud object, sending it falling toward the inner solar system. As it approaches the Sun and heats up, its ices sublimate, creating the characteristic glowing coma and tail that make comets visible from Earth. In the first few 100 million years after Earth formed, our planet was a hellish place. The surface was molten, heated by the energy of countless impacts and by the decay of radioactive elements in Earth's interior. The atmosphere, if it existed at all, was likely a mixture of water vapor, carbon dioxide, and nitrogen, with no oxygen. The young Earth was constantly bombarded by asteroids and comets. Clearly, this period, lasting from about 4.6 to about 3.8 billion years ago, is called the Late Heavy Bombardment. Some of these impacts were so energetic they may have vaporized any early oceans that had begun to form, repeatedly sterilizing the surface. Yet these impacts also delivered crucial materials to Earth. Many comets and asteroids contained water ice and organic molecules, the carbon-based compounds that would eventually become the building blocks of life. The water that fills Earth's oceans today may have been delivered at least partly by cometary impacts during this violent period. By about 4 billion years ago, Earth had cooled enough for liquid water to persist on its surface. The first oceans formed, though they were likely much more acidic and contained higher concentrations of dissolved iron and other metals than modern oceans. The sky would have appeared orange or pink due to methane in the atmosphere. Somewhere between 4.4 and 3.8 billion years ago, in these early oceans, or perhaps in hydrothermal vents on the ocean floor, chemistry became biology. The exact mechanism remains one of science's great unsolved mysteries. We know it happened, but not precisely how or where. The first living things were almost certainly single-celled organisms, far simpler than even modern bacteria. They would have lacked the complex cellular machinery that modern cells possess. Perhaps they were little more than self-replicating molecules, enclosed in simple membranes, capable of extracting energy from their environment and making crude copies of themselves. These first organisms did not use oxygen. There was essentially no oxygen in Earth's atmosphere at that time. Instead, they derived energy from chemical reactions, perhaps using hydrogen, methane, or iron compounds. They lived in environments that would be toxic to most modern life forms. For perhaps 1 billion years, life remained microscopic and simple. But around 2.7 billion years ago, some organisms evolved the ability to harvest energy from sunlight through photosynthesis. This was a transformation as significant as any in Earth's history. The first photosynthetic organisms, called cyanobacteria, used sunlight to convert water and carbon dioxide into sugars, releasing oxygen as a waste product. At first, this oxygen did not accumulate in the atmosphere. It reacted with dissolved iron in the oceans, causing iron to precipitate out and sink to the seafloor. These precipitated iron deposits formed massive banded iron formations that we can still see today in ancient rocks. They represent the largest iron ore deposits on Earth, billions of tons of iron laid down over hundreds of millions of years as early photosynthesis transformed ocean chemistry. Moment. Eventually, around 2.4 billion years ago, the ocean's dissolved iron was exhausted. Oxygen produced by cyanobacteria began accumulating in the atmosphere. This event is called the Great Oxidation Event, and it fundamentally transformed Earth's environment. For most organisms living at the time, oxygen was toxic. The Great Oxidation Event likely caused a massive extinction of organisms adapted to the oxygen-free environment. But it also created opportunities. Oxygen-based metabolism is far more efficient than anaerobic processes, releasing much more energy from the same amount of food. Organisms that could tolerate or utilize oxygen gained enormous advantages. Over time, aerobic organisms, those using oxygen for metabolism, became dominant. This more efficient metabolism would eventually power the evolution of complex, multicellular life. Between 2 billion and 1 billion years ago, the first eukaryotic cells evolved. Eukaryotes are cells with internal compartments, including a nucleus that contains genetic material. Modern plants, animals, and fungi are all made of eukaryotic cells. Eukaryotic cells likely evolved through a process called endosymbiosis. Ancient bacteria were engulfed by other cells, but not digested. Instead, they formed a symbiotic relationship, living inside their host cells and providing energy. The mitochondria in our cells today, the organelles that produce energy, are descended from these ancient bacteria. For billions of years, life remained single-celled. Around 1 billion years ago, some organisms began forming colonies, with cells cooperating rather than living independently. This was the first step toward true multicellularity. Around 540 million years ago, complex multicellular life suddenly diversified in an event called the Cambrian explosion. Within a relatively short time, perhaps 20 to 30 million years, most major animal body plans appeared in the fossil record. This included the first animals with hard shells and skeletons, which preserve more readily as fossils. The causes of the Cambrian explosion are still debated. Rising oxygen levels likely played a role, as complex animals require higher oxygen concentrations than simple organisms. The evolution of predation may have driven an evolutionary arms race. Whatever the causes, life's complexity increased dramatically during this period. Over the following 500 million years, life colonized nearly every environment on Earth. Plants moved onto land around 450 million years ago, followed by animals. Forests developed, insects evolved flight. Fish evolved into amphibians, amphibians into reptiles, reptiles into both mammals and birds. There were setbacks. Earth has experienced at least 5 major mass extinctions, events in which more than half of all species died out. The largest, around 252 million years ago, killed perhaps 90% of all species. Yet life has always recovered, often evolving in new directions after extinctions cleared ecological niches. The most recent mass extinction occurred 66 million years ago, when an asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear weapons, triggering wildfires, tsunamis, and a global winter that lasted years as dust blocked sunlight. The dinosaurs, which had dominated terrestrial ecosystems for over 160 million years, went extinct in this event. But small mammals survived, and in the aftermath, they diversified rapidly into the ecological niches left vacant. Within 10 million years, mammals had evolved into many forms, from tiny shrews to creatures the size of modern deer. Around 6 million years ago, the human lineage diverged from our closest relatives, the chimpanzees and bonobos. Our ancestors began walking upright, freeing their hands for tool use. Brain size gradually increased. Language developed. Culture emerged. Modern humans, Homo sapiens, evolved in Africa around 300,000 years ago. For most of our species' history, we lived as hunter-gatherers in small groups. Then, around 12,000 years ago, some human populations began domesticating plants and animals, developing agriculture. This allowed larger, more complex societies to develop. And here we arrive at the present moment. A species that evolved on one planet now understands that planet's place in a solar system, that solar system's place in a galaxy, that galaxy's place in a universe 13.8 billion years old. We are the universe's way of knowing itself, at least in this small corner of space. From the initial singularity to the present moment, the story has unfolded through predictable physical laws. Gravity pulled matter together. Nuclear fusion ignited stars. Heavy elements formed and scattered. Planets accreted. Chemistry became biology. Evolution shaped life into ever more complex forms. And eventually, consciousness emerged. This is where we stand, products of 13.8 billion years of cosmic evolution, briefly aware of our origins before we too pass into history. But the story does not end here. The universe continues its journey into the far future. Looking forward from our present moment, 13.8 billion years after the beginning, the universe faces a long and slowly darkening future. The processes that have shaped cosmic history will continue, but the overall trajectory is one of expansion, cooling, and gradual decline in activity. The Sun, now approximately halfway through its main sequence lifetime, will continue fusing hydrogen into helium for another 5 billion years. During this time, it will slowly brighten, increasing its luminosity by about 1% every 100 million years. This brightening will have profound consequences for Earth. Within about 1 billion years, the Sun's increasing luminosity will evaporate Earth's oceans. The increased solar radiation will enhance the greenhouse effect, eventually leading to a runaway situation where water vapor in the atmosphere traps heat, causing more evaporation, trapping more heat. Earth's surface temperature may exceed 1,000 degrees Celsius. By 3 to 4 billion years from now, Earth will likely resemble Venus today, a barren, scorched world with a thick carbon dioxide atmosphere. Any life that exists on Earth will either need to adapt to increasingly extreme conditions, migrate to other worlds, or face extinction long before the Sun's main sequence phase ends. In approximately 4 billion years, the Andromeda galaxy will collide with the Milky Way. Despite what collision suggests, individual stars will rarely actually hit each other. Space between stars is simply too vast. But the two galaxies' gravitational fields will interact dramatically. The collision will unfold over billions of years. The galaxies will approach, swing past each other, and fall back together multiple times before finally merging. Gas clouds in the two galaxies will collide, compress, and trigger enormous bursts of star formation. The night sky, viewed from any surviving planets, will display spectacular irregular structures as the galaxies distort each other. Eventually, around 6 billion years from now, the Milky Way and Andromeda will merge into a single giant elliptical galaxy. Astronomers have already nicknamed this future galaxy Milkomeda. Our solar system, if it still exists, will likely be flung into a different orbit within this new galaxy, perhaps much farther from the galactic center. Around 7 billion years from now, the Sun will exhaust the hydrogen in its core. Fusion will cease there, and the core will begin contracting under gravity. This contraction will heat the core and trigger hydrogen fusion in a shell surrounding it. The energy from this shell burning will cause the Sun's outer layers to expand dramatically. The Sun will swell into a red giant, growing perhaps 100 to 200 times its current radius. Its surface will cool to around 3,000 degrees Kelvin, giving it a reddish hue, but its total luminosity will increase thousands of times. Mercury will almost certainly be engulfed and destroyed. Venus will likely be engulfed as well. Earth's fate is less certain. As the Sun loses mass through stellar winds during its red giant phase, Earth's orbit will expand outward. Whether this expansion will be enough to save Earth from engulfment is unclear. Current models give varying predictions. But even if Earth avoids being swallowed, its surface will be heated to temperatures that vaporize rock. The Sun will spend approximately 1 billion years as a red giant, fusing hydrogen in a shell around its helium core. Eventually, the helium core will contract and heat until it reaches 100 million degrees Kelvin, hot enough to fuse helium into carbon and oxygen. Helium fusion ignition may happen suddenly in an event called a helium flash. The core will briefly release as much energy as an entire galaxy, but this energy will be absorbed by the outer layers of the star rather than escaping into space. The flash will last only seconds, but will fundamentally change the star's structure. After the helium flash, the Sun will settle into a period of stable helium burning in its core, while also fusing hydrogen in a surrounding shell. It will shrink somewhat from its peak red giant size. This phase will last approximately 100 million years. When the helium in the core is exhausted, leaving a core of carbon and oxygen, the Sun will expand again. But the Sun is not massive enough for its core to reach the temperatures needed to fuse carbon. The core will simply contract into an extremely dense state, while the outer layers expand further than before. During this final expansion, the Sun will lose mass through increasingly powerful stellar winds. Its outer layers will gradually drift away into space, forming a planetary nebula, a glowing shell of gas surrounding the hot, exposed core. The nebula will shine for perhaps 10,000 years before dispersing into the interstellar medium. What remains will be a white dwarf, the exposed core of the Sun, about the size of Earth, but containing roughly half the Sun's original mass. This white dwarf will no longer undergo fusion. It will simply cool slowly over trillions of years, gradually fading from white to yellow to red to eventually black. The white dwarf will initially be extremely hot, perhaps 100,000 degrees Kelvin at its surface, though its core may be much hotter. It will glow brightly despite its small size. Over billions of years, it will radiate away its heat, cooling and dimming. After approximately 10 trillion years, the white dwarf Sun will cool to the point where it no longer emits visible light. It will become a black dwarf, a cold, dark sphere of carbon and oxygen, a stellar remnant that has reached thermodynamic equilibrium with the cosmic background radiation. The universe, however, is not yet old enough for any black dwarfs to exist. By 100 trillion years from now, most of the universe's star formation will have ceased. The gas necessary to form new stars will have been consumed or locked up in stellar remnants and planets. The universe will contain mostly red dwarfs, the smallest, longest-lived stars, along with white dwarfs, neutron stars, and black holes. The red dwarfs will continue shining. The smallest of them have lifespans exceeding 10 trillion years. The last red dwarfs will not exhaust their fuel until perhaps 100 trillion years from now. After that, no ordinary stars will remain in the universe, only stellar remnants. Between 100 trillion and 1 quadrillion years from now, the universe will enter what is sometimes called the Degenerate Era. All normal stellar fusion will have ceased. The universe will be illuminated only by the gradually fading light from white dwarfs and brown dwarfs, failed stars that never quite achieved fusion. Occasionally, two white dwarfs or brown dwarfs will collide, briefly creating a new star that burns for a short time. These collisions will become increasingly rare as galaxies expand and objects drift apart. The universe will grow darker and colder, its temperature dropping ever closer to absolute zero. Around 1 trillion to 1 quadrillion years from now, galaxies themselves may begin to dissolve. Stars in a galaxy are bound by gravity, but occasionally Gravitational interactions, particularly close encounters between stars, can accelerate a star to escape velocity. Over trillions of years, these ejections will gradually deplete galaxies. Most stars will eventually be flung into the vast spaces between galaxy clusters. The remaining stars will fall inward, accumulating around the central supermassive black hole. Eventually, most will either be ejected or swallowed by the black hole. By 1 quintillion to 1 sextillion years from now, protons themselves may decay. This is speculative. Proton decay has never been observed, and current experiments show that if it occurs, the proton lifetime must exceed 10 to the 34 years. But many theories predict that protons are not absolutely stable. If protons decay, all ordinary matter will gradually disintegrate. White dwarfs, neutron stars, planets, asteroids, all objects made of atoms will slowly evaporate as their constituent protons decay into lighter particles. The universe will contain only black holes, electrons, positrons, photons, and neutrinos. Black holes, however, are not eternal. In 1974, Stephen Hawking demonstrated that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly lose mass and eventually evaporate completely. The evaporation time for a black hole depends on its mass. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate. A supermassive black hole with 1 billion solar masses would take 10 to the 98 years. These timescales are so long that even describing them feels abstract. But given enough time, all black holes will evaporate. By perhaps 10 to the 100 years from now, a Google years, even the largest supermassive black holes will have evaporated away, leaving behind only the faintest whisper of particles and radiation. What remains is sometimes called the dark era or the photon age. The universe will contain only photons, leptons, and possibly other very low-mass particles, all at temperatures unimaginably close to absolute zero. Density will be extraordinarily low, perhaps 1 particle per cubic light-year of space. Through all of this, the universe will continue expanding. Current observations indicate this expansion is accelerating, driven by dark energy, a mysterious component that appears to exert negative pressure on space itself. If dark energy remains constant, the expansion rate will increase over time. In this scenario, called the Big Freeze or heat death, the universe will expand forever. Temperatures will approach absolute zero asymptotically. Entropy will increase toward a maximum. Eventually, even the cosmic microwave background radiation will be stretched to wavelengths larger than the observable universe itself. There is another possibility. If dark energy increases over time, the expansion could accelerate more and more rapidly, eventually overwhelming all other forces. This scenario is called the Big Rip. Approximately 100 billion years from now, in this model, the expansion would accelerate so drastically that it would tear apart galaxies, then solar systems, then planets, then molecules, then atoms, and finally even atomic nuclei. Alternatively, if dark energy weakens or reverses, the universe's expansion could slow and eventually reverse. The universe would begin contracting, entering a big crunch. All matter and energy would eventually collapse back toward a singularity, perhaps giving birth to a new universe in an endless cycle of expansion and contraction. Current observations favor the Big Freeze scenario, with eternal expansion driven by dark energy. But the distant future is fundamentally uncertain. We can only observe the universe's behavior over the past few billion years, an infinitesimal fraction of cosmic time. In any of these scenarios, the universe we know, filled with stars, planets, and life, represents a brief, special epoch. We exist during the time when stars shine, when complexity can emerge, when the universe is neither too hot nor too cold for interesting processes to occur. This epoch will last perhaps 100 trillion years in total, from the first stars to the last. And here we find ourselves, 13.8 billion years after the beginning, about 1/10,000th of the way through this special epoch. The first generations of stars have lived and died, scattering the elements necessary for planets and life. Our Sun, a later generation star enriched with these elements, shines steadily in a quiet spiral arm of a typical galaxy. Around this Sun orbits a rocky planet, the third from the Sun, with conditions that have allowed liquid water to persist on its surface for billions of years. On this planet, through processes we are still working to understand, chemistry gave rise to biology. Simple, self-replicating molecules evolved into cells, cells into multicellular organisms, organisms into ecosystems of staggering complexity and beauty. And in the last few million years of the universe's 13.8 billion year history, in the last few eye blinks of cosmic time, one species on this planet developed the capacity to look outward and ask questions, to wonder about origins, to reconstruct history, to peer backward in time by looking at distant galaxies, to understand, at least partially, the universe's past and project its future. We are made of atoms forged in the cores of dying stars, atoms that drifted through space for billions of years before gravity collected them into the cloud that formed our sun and planets. We are, quite literally, the universe contemplating itself. We are the mechanism by which the cosmos comes to know its own story. This knowledge brings both wonder and melancholy. Wonder at the magnificent scope of cosmic history, at the intricate web of causes and effects that led from the first fraction of a second to this present moment. Melancholy at the transience of it all, at the knowledge that everything we know will eventually fade. But perhaps there is comfort too, in the knowledge that we are part of something vast and ancient, that the carbon in our muscles, the calcium in our bones, the iron in our blood, all of it connects us to events billions of years old and thousands of light years distant. We are not separate from the universe, but deeply embedded within it. And in this present moment, in this brief window when stars shine and complexity flourishes, we have the extraordinary privilege of understanding, even partially, where we came from and where we are going. We can look up at the night sky and know that we are seeing light that began its journey millions or billions of years ago. We can look at the cosmic microwave background and see the universe as it was 380,000 years after its birth. We stand at a unique point in cosmic history. Behind us lies 13.8 billion years of expansion, cooling, structure formation, and increasing complexity. Before us lies a future measured in trillions of years, slowly winding down toward darkness and simplicity. We exist in the brief, bright interval between initial chaos and final stillness. The universe's story is far from over. Stars will continue forming for trillions of years. Life may arise on countless worlds we have not yet imagined. Intelligence may emerge, flourish, and fade many times in many places. The universe will continue surprising us, revealing new depths and complexities we cannot yet foresee. But for now, here we are, witnesses to a moment in the vast unfolding, participants in the universe's long conversation with itself, temporary arrangements of ancient atoms, aware enough to trace our own history back to the very beginning and forward to the very end. And perhaps that is enough. To know the story, to understand our place in it, to stand under the stars with knowledge and wonder, aware that we are both infinitesimally small and profoundly connected to everything that has ever been or ever will be. The universe began in unimaginable simplicity, a single point of infinite density. It will likely end in unimaginable simplicity, an infinite expanse of near nothingness. Between these two simplicities, briefly, there was complexity. Stars, planets, life, consciousness, understanding. And here, in this middle period, in this moment of maximum complexity and minimum entropy, we tell ourselves the story. We piece together the history written in starlight and stone, in cosmic background radiation and radioactive decay. We reconstruct the past from fragmentary evidence and project the future from known laws. The story we tell is one of transformation, from energy to matter, from matter to stars, from stars to heavier elements, from elements to planets, from planets to life, from life to thought, from thought to understanding. Each stage building on what came before, each transformation opening new possibilities. This transformation continues. We do not know what comes next. Perhaps life will spread beyond Earth, seeding itself across the galaxy. Perhaps intelligence will evolve in forms we cannot imagine. Perhaps consciousness will find ways to persist, even as the stars grow cold. Or perhaps not. Perhaps we are a brief flicker, soon to fade. Either way, for this moment we are here, aware, understanding, telling the story, and in the telling, participating in the universe's grandest project, the project of knowing itself, of transforming from unknowing matter into knowing mind, of becoming a mirror in which the cosmos can see its own reflection. So rest now under the ancient light of distant stars. Rest knowing you are part of something vast and beautiful and strange. Rest knowing your atoms have journeyed for billions of years to be exactly where they are. Rest in the quiet certainty that the universe, in you, has learned to understand itself. The story continues, as it has for 13.8 billion years, as it will for trillions more. But for now, in this moment, the story has been told. From beginning to end, from the first instant to the final darkness, the arc is clear. And you have heard it. Sleep well, knowing the universe's history. Dream of stars being born and dying, of galaxies colliding, of time stretching endlessly forward and back. Dream of the deep connections binding everything to everything else. Dream of infinity. The universe is vast, and you are small. But you are made of the same substance as stars, and you carry within you the capacity to understand it all. That is perhaps the universe's greatest achievement. That is the meaning, if meaning there is. To know, to understand, to be aware of the whole magnificent sweep. Rest now in that knowledge. The universe will continue its long journey, expanding into darkness, but carrying always within it the memory of this bright moment when minds arose and understood. Rest easy. The story is told.